We cooking? Yep. All right. So, are we up here? For those of you who have had me before, you know who I am. For those of you who haven't, I'm Dr. Littman. You can call me Dr. Littman, Mike, Yo Fatty. I don't really care. If you haven't gathered yet, I am pretty laid back. The syllabus will be up by tomorrow morning. I'll put your first assignment up on Angel probably during the break today. We'll go for about an hour and 45 minutes, 2 hours. Natural breaking point, then take about a 30-second break. Take a breather. So typically I start winding things down by about 9:30-ish, but I don't know. I usually go till about 10, so just deal.
We have no choice.
Yeah, it's actually funny. When I first started teaching 15 years ago, I was always so nervous. I couldn't fill a class, even 50-minute classes. I would go 37 minutes, run out of crap to say. Now I can't. I just don't shut up. I know class is over when the students start packing up, and they're usually going. They give me 2 minutes leeway. All right. So for this class, I'll go ahead and put on a slide what the grade breakdown will be. It'll also be in the syllabus. So grades, you will have 60% of your grade is homework.
Yay.
Now, homework comes in two forms. Comes in the form of programming assignments and comes in the form of papers. Okay? So 60% of your grade will be those things.
So 30-30 each.
You can think of it like that if you want. Whether they're all worth 60% or each of them is worth 30%, it comes out to the same. All right. So then 20% of your grade. Quizzes. This is something new for me. These will be in-class quizzes. Totally nuts. Yeah. All right.
Weekly quizzes?
Huh?
Weekly?
Maybe.
We meet weekly, so it's
Yeah.
probably...
I would say more than likely, the beginning of each class you will have a quiz, but not necessarily at the beginning. You might have one after a break. I might even do 2 quizzes in one class. It really just depends on how mad I am and how much Portillo's is in my body.
If I had extra gas, I would just go and drive and do some myself, so we won't have to do it.
20% final exam, which will be in class. But I'm going to design it to take about an hour. So it'll be the final hour of our final class. And it will not take anything that we learn in the final class into consideration.
So, it won't be nothing like that final project we had to do last time.
Well, it's going to be a written test, and then you'll also have a final homework assignment. Completely unreasonable, I know.
Dude, hold on, we'll wait. Changed around the whole game plan. We should meet before.
No, but see, this is the harder version of the class, right?
That's just rude. That's what it is. We already worked hard in the first one.
Now, what I'll try to do is maybe make the papers relatively short,
Thank you.
since this one is a little bit more programming focused. So maybe it'll be 8 to 12 pages instead of 12 to 15. Yeah.
So the final exam will be like programming or questions?
Mostly programming. Well, actually, that's not even fair to say. The final exam will be, let's assume there's 10 questions on it. Probably 3 or 4 of them will be actual programming questions. The rest of them will be concepts.
Okay.
What is this? What is that? Because I want it to take about an hour. And typically, writing programs by hand for beginning programmers is a time-intensive thing. So, for instance, I just gave an exam in a similar class, a midterm, last week, and there was 2 programming questions and 8 questions dealing with other stuff. So very possibly that was what your exam would look like. Okay? Something along those lines. I try not to make my exams a time pressure type thing.
But yeah,
If
you're
you-
doing an hour.
Well, I'll design it to take like 40 minutes.
Oh, okay.
You know, so if you're not done in an hour, that means you're stupid. That's what.
You don't want me to comment on that. You want me to keep my mouth shut.
All right.
Jesus be with me.
Okay. So questions on that? I'll put that into a formal syllabus. It'll be up tomorrow morning. But that's the grade breakdown for the class.
While you're in your hot tub, it's no longer hot.
No, I have to turn it back off and put the tape back on. They're coming at 8:30. They can't know. They'll yell at me.
When they put their hand in the hot water.
They never even lifted the lid today. They know I'm putting water in it. They don't. I might have to come clean. We'll see.
You might.
All right. So let's kind of pick up where we left off from the 535 class, but I'm going to do a little bit of overlap. Starting point is, what this class is really about is something called data structures. Okay, so we call this programming 2 or whatever the stupid name is for the class, but really it's about taking what we learned in our beginning programming class, the basics of programming, and saying, okay, the logic of programming has taken us this far. Now, where can we go to take it to the next step? And what happens is we start running out of tools that are built into the language, and we need to start writing our own tools. Or we need to at least understand some more advanced tools that are built into the language before we can just go and start using them. Okay? So a data structure is a structure for holding data. All right? So if we try to think about this in terms of real life or something, if you go and buy a container from Target or something like that, that's a container you could put crap into, right? Now, there's a generic container that's just a bucket. You can just throw whatever you want in there and it's not organized in any sort of interesting way, right? Then they have like those specialty containers for shoes. You seen those? Where you probably have one of those, don't you? Do you? You like shoes? You got a bunch of shoes? I have flip-flops. Look at that.
Got a bunch of flip-flops.
I do.
And purses.
I don't have purses.
No, I'm saying I have one for purses.
Oh, you have an organizer for purses?
Mhm.
That's weird.
That's wrong.
So in any case, when you buy those specialty organizers, they have cubby holes in them to hold very specific things. So when you use them, the things are organized in some sort of special way, right? So when we talk about data structures, we're talking about creating objects, creating structures for holding data in interesting ways. And when we hold data in interesting ways, that then lends itself to us being able to manipulate and do stuff with data that we may not have either been able to do before or at least not as easily. We couldn't do it before. Okay, kind of makes sense? Now, we already know one data structure. And we're going to start off with that. We're going to review that and how they work and talk about some of the strengths and weaknesses. And that's something called an array. Okay? So, remember arrays? We dealt with arrays, right? Okay? What is an array? Make this our first quiz.
Please.
You don't remember what an array is?
I do, but it's just.
Seems like that should be an easy quiz. So
Okay,
what would you say? What is an array?
Array is. Gosh, I don't know where am I supposed to put this in normal people terms.
You got it?
I know it's Arabic.
You know in Arabic? All right, give me the answer in Arabic.
Let's move on.
Gesundheit.
Oh my goodness.
It's kind of like arrangement of objects that contains objects, numbers, letters.
Okay.
Like
Like
buckets.
it can start with zeros.
Okay, arrangement of stuff.
Yeah.
You're calling them objects. Doesn't have to be objects. It could also be primitive types. What's a primitive type? Remind me.
Integers.
Okay. Yeah, that's an example of a primitive type.
Yeah.
Ints, chars, booleans, floats, doubles, bytes, shorts, longs. What is a primitive type? Those are examples of primitive types.
Kind of data.
A data type
It is a data type.
that is a whole that comes out to be be a whole number or like without decimals?
What?
I don't know.
That's an int.
I know.
Primitive types. Man, we need to throw a couple things in here. Hold on a second, people.
Apparently it was
There's been some leakage. There's been some leakage. Primitive type. It's a data type built into the language that is only capable of holding a value. So examples of these are byte, short, int, long, char, float, double, boolean. Those are our Java primitive types. Okay. Now, the important thing about this is this concept of it only being capable of holding a value, as opposed to object types, which can potentially hold can hold 0 or more values and potentially do more through methods and things like that. Okay, so primitive types are the bare bones basic way of storing something, and all it can do is hold a value. All right. Now, an array would be a collection of like data types. It's a starting thing. By like, I mean a bunch of integers, or a bunch of chars, or a bunch of strings if you're dealing with objects, a bunch of houses if we wrote our own house objects, something like that.
Can it be like mini, like double and end?
No, they have to be like. You can't have an array of ints and store some doubles.
So it's like, say we were.
So here, I'll capitalize this guy.
We are in the suburbs, so it's like a subdivision.
The suburbs.
A subdivision of
What?
Houses, like an array.
What?
It's like a subdivision of houses.
In what way?
All of these houses are houses.
Oh, okay.
Yeah,
I got you.
I'm
So
putting it
a
in-
subdivision, which is a collection of houses, would be an example of an array of houses.
Yes.
I'm
There we
okay
go.
with that.
Thank you.
I mean, I really kind of like the way I said it better.
You did say it much better, but
I have a PhD.
You know what? You can do all the schooling you want.
Well, you're still sitting in class.
I said at this point, after December 13th,
This is it?
I'm done.
Aren't you getting ready to start a PhD?
Fall.
Yeah, what are you thinking, man?
Yeah. Be on your craziness.
Seriously, you don't want to be there. Who is this their first class with me? Who's never had me before?
Oh, so y'all probably think we are.
A little bit of an interesting class, huh? Giving answers in Arabic. Probably a cricket fan too, aren't you?
Yeah. You can tell.
Is this like a cricket sweatshirt you got on?
No, it's Concordia.
Oh.
But
He's only wearing it because they gave it to him for free.
Oh, wait. How did you get a free sweater?
It's not free.
Whatever. I think it is.
You are a cricket fan, aren't you?
Yeah, you are. Oh, you're a
It's for
football fan.
Indians, not for us.
Huh?
It's for the Indian people.
I thought cricket was everywhere except the United States.
No,
Pretty
just
much.
India.
Huh?
Just India.
It was India?
No, because they do it in London too.
Yeah, seriously, it's all made up.
They have a Lord's big old field for
Are
cricket.
you Saudi?
Yes.
All of y'all Saudi. I don't even know what. Like,
Oh, y'all. All this is being recorded. I do put all my lectures up online, by the way, so you can relive these events. All right.
I didn't say anything.
Yeah, several of my classes get very interesting. Okay. So arrays, collection of like data types. Now, you asked the question, can we put like ints and doubles in the same array? Technically, no, not directly, but we can create our own object type. And maybe our object type knows how to hold either an int or a double, and then we can have an array of those objects. Okay, so we can sort of kind of pull it off. All right, but the general version. See, we're trying to introduce this idea of our first data structure, which is something we already know, but we never really thought of it as a data structure. We just thought of it as, a new way of storing crap. Now we're kind of putting a name to that. All right, so arrays are collections of like data types. They are stored in contiguous
What's that?
memory. What does contiguous mean? You had this class?
I had the one before this. You didn't use that word.
Oh, I
before.
absolutely used that word.
Oh, well then, it was a
Like
year ago.
Arrangement in the memory for the address.
Yeah, they must be in a row.
Yeah.
So contiguous means right next to each other in memory. Okay, it's important for arrays, and we'll review that today since seemingly you guys don't remember anything.
Hey, don't go there.
It's true.
Don't
All right,
me.
so it's stored in contiguous memory. So what's good about arrays? Well, they're fast. Arrays are also memory inefficient. Okay, so they're very quick to go through an array because we can mathematically walk through an array, and I'll show you that here in a minute. But arrays are memory inefficient because they require contiguous memory. Both of those things are related. The reason they're fast is because they're stored in contiguous memory, which allows us to calculate the various buckets of an array. Okay, and I'll show that to you. So this would be a positive of an array. Arrays are fast. This might be a negative array about arrays. Arrays are memory inefficient. Okay, and those are two things we kind of want to think about as we're going through this. And when we get to my guess is we'll probably introduce I'm going to say upgrade to arrays, but it's not really fair to call it that. Right before we go to break, and then we'll spend most of the second half of today talking about them, we're going to be looking at something called a linked list, which are similar to arrays, but take some other choices. Okay? So, arrays are memory inefficient. So let's look at this. Let's go over to Eclipse. Let's write some code for an array first. See it, and then we'll go back over to the slide set and look at what that looks like. I'll also share the slide set with you on Angel. It's a new thing with the new iCloud Drive thing. You get the live updates to it or something like that. So I don't know. So in Eclipse, I'm going to create a new project. Actually, I'm not going to do that. I'm going to create a new Java project. I could have done it from there, but whatever. New Java project. I'm going to call this guy 537, you said? Fall 2014. That's my project name. And then I'll go ahead and create a new class in here. And I'll call this guy driver. And we'll go ahead and write our quick little hello world program. We should all know how to write a hello world program, right? How many of you have never had Java before, since you haven't had me before? But you've had another language. So everybody in here could write a hello world program in Java?
So 10 years ago.
Huh?
I have Java 10 years ago.
10 years ago?
10. How old are you?
He's 13. He's a prodigy.
Mhm.
So you don't want me to give you a quiz for hello world. Is that what you're saying? All right. So public static void main. String array elephant. All right, so there's our hello world program. I always start off our projects with that. That way you know everything, all the guns are firing. We hit play. We see this guy runs and prints out hello world. All right, functioning program, great. Now, one thing I might recommend, I have been known to give hello world quizzes before to test programming competence. Every one of you in here, by next class, should be able to write that perfectly with 0 errors by hand. The only thing you can change here is this does not have to be called elephant. You can call it whatever you want. All right? So traditionally it's called args. But every one of you should be able to write this because this should be your go-to move whenever you start a program. As soon as you dive in, we're going to immediately start writing the hello world starter, and then we'll start moving stuff from there. Okay? I would call it a high likelihood that I will quiz you on this at the very beginning of next class. You might then also have a second quiz sometime in the next class. Who knows? Who knows? All right. So here's our hello world program, but now we're going to go ahead and create an array. So syntax for an array. We're going to go ahead and create an array of integers. So we're going to create a collection of int data types. So int array is going to be my type. Now just as a quick reminder, general syntax in Java for creating a variable is type varname equals value, semicolon. Right? That's the generic syntax in Java for creating a variable. It's also the generic syntax in C# for creating a variable. It's also the generic syntax in C++ for creating a variable. It's also the generic syntax in C for creating a variable. It's also the generic syntax in Objective-C for creating a variable. So once you know one language, you know them all. Except Visual Basic. Visual Basic is a stupid language.
Good thing I don't program with it anymore.
Really? Did you quit that job? They can you?
No, I got a promotion.
What are you coding now?
I am not coding. I'm a project manager.
Oh, big surprise.
Hater.
All right. So our type for this guy is going to be an integer array. So this is the opening close square brackets. I'm going to name our variable AR. This guy's going to be a new integer array, and I'll make it capable of holding 10 things. Okay? Actually, just for the sake of my slide, let me be capable of holding 5 things. All right, so right off the bat, let's look at what this just made. Okay, so that's the syntax for creating a new variable named AR that indeed is a array of 5 things. Let's draw a picture because I like drawing pictures. I know, it's one of my hobbies.
For some reason, my what-you-call-it isn't working.
Who?
Eclipse. It keeps saying something about Java. I've upgraded my Java and it's still not
Okay, so something like this just got created. Good for now. All right, and then we're going to have our variable. Here's AR, and we'll change this up real quick. This is going to be a green box. Perfect. Who?
Said you really love those 3 colors.
Do I?
Yeah, you always do.
Ah! It could just be that those are the ones they provide me up here when I click one of these boxes.
Because you said you was orange or silver.
I'm getting there.
Okay.
All right. So this is essentially what an array looks like. So we have a collection of 5 individual buckets, each capable of holding an integer. All right? These buckets are indexed from bucket 0 to bucket 4. So even though there's 5 buckets, it's a 0 indexed array. So that's 0, 1, 2, 3, and 4. Okay? Now, the reason that these guys are, that arrays are fast, I'm about to show you. But before I finish drawing my picture here, what will print out? There. What will the output of this program be?
It will be whatever is in bucket 5 of variable
The
A.
address,
Memory address.
the first one.
Okay? So this is going to be a really weird looking memory address thingy. Okay? And notice how the Java virtual machine does addressing for arrays. So this is saying this is an array of integers. that lives at this fake memory address that is an abstraction of your actual memory on your computer. Doesn't really matter if you know how to read these. I'm just more trivia knowledge here. Okay? But the point is that AR holds a memory address. The new keyword, this dude right here, just remember, here is our generic syntax for creating variables. Type, variable name equals value. So everything after the equal sign here is the value associated with this array. This value is going to be produced using the new keyword, along with, we're going to loosely call this a constructor for right now. Okay? The new keyword I usually refer to as our real estate agent. It goes out to the operating system, or in this case, the Java virtual machine, which then goes to the operating system and says, hey, I need some memory. How much memory do you need? I need enough memory to hold this many of these guys. How big's an int in Java? Who?
Like 8 bits.
8 bits?
4 bits.
12 bits?
No, 4.
4 bits.
Yeah.
4 bits or 4 bytes?
No, 4 bits.
4 bits. Okay?
It's a 1 byte.
What's the biggest number that we can hold in a 4-bit value? What's a bit?
65,000.
A bit is a 0 or a 1, right? That's what a bit is. What's a byte?
8 bits.
8 of those. So if we only have a 4-bit number, what's the biggest number we can hold? 1111. That's the 1's place, the 2's place, the 4's place, the 8's place. So 8 plus 4 plus 2 plus 1? 15? So, can integers hold values greater than 15?
Yes.
Can integers hold negative values?
Yes.
No.
Oh. So if they can hold negative values, then we only get to use 3 of your bits for the actual value.
This is 8.
So you think it's 8 bits? Okay, for an int?
Yes.
What's the, if we're dealing with signed numbers, that is, we can hold positive and negative numbers, what's the biggest number we can hold in a 8-bit number? That is to say, what's the biggest number I can hold? That's 7 bits. We're going to use one of the bits for the sign. What's that number?
65,000.
Should be
63.
should be 128.
Yeah, 100.
128.
He just agreed with you.
This is the 1's place, the 2's place, the 4's, the 8's, the 16's, the 32's, the 64. So 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1. Is it 127 or 128? 127?
Yeah.
All right. Close enough. Okay, so not 8 bits. Let's go with 32 bits. Okay, so an int in Java is 32 bits. It's a 32-bit signed integer. 32-bit signed integer. It can hold values in the range of negative plus or minus 2 billion, give or take. So it's plus or minus 2 to the 31st power is the range that an integer can hold. Not that important for this example. This example says I need this many 32-bit buckets, or 4-byte buckets. A byte is 8 bits, 32 bits would be 4 bytes, get it? So that means I need 20 bytes of memory in a row. Why in a row? Because arrays, contiguous. All right? So the new keyword says, go and find me 20 bytes in a row in memory, and you come back and tell me where it starts. So what I printed out right here is the value of AR, which is the value that AR holds, because AR is a pointer, which points to the beginning of this array. All right, so AR is actually a primitive type variable called a pointer. Now, Java officially doesn't have a pointer type. C, C++ do, C# sort of does through the use of unsafe code blocks. Objective-C also just sort of does because actually Objective-C has made a pretty similar choice as Java has, but just they throw more syntax in there.
Question. Are we still doing the Objective-C in this class?
Yeah, we'll do some.
Oh.
Yep. It's last 2 weeks. We'll do some stuff.
Isn't that the building app or something?
Yeah,
Okay.
we'll do some stuff.
Yeah.
All right. So, in any case, is that from that commercial?
Yes. Too much TV.
It seems like the school is very busy tonight for them being on fall break.
They're on fall break.
Yeah.
They're leaving.
Huh?
They're leaving.
They're leaving? Yeah, I guess that could be.
Fall break for what?
I don't know.
We never had a freaking fall
I
break.
gave all my midterms and now they leave.
Losers.
So, well, imagine how I feel after come and teach this class when fall break's supposed to start.
Excuse you.
All my class is supposed to be done by 4 p.m. today.
You could have did this online and then sent it to us and told us to sit there for 4 hours at home and do it.
I'm supposed to sit there and talk to myself for 4 hours at home?
Hey, you the one that's complaining.
My wife says the same thing. Okay, so in any case, AR is a pointer. Pointers are primitive type variables capable of holding a memory address. That's what a pointer is. Primitive type variable capable of holding a memory address. So for our simple example here, we're going to say AR holds the memory address 100. That is to say, when I run this, it prints out 100 instead of that. For my little example. Okay? This is the value that AR currently holds. A memory address. All right? For my example, saying 100 makes more sense because I can't count easily in hex. Actually, the creepy thing is I actually can count fairly well in hex, but that's a whole nother problem. So, you trying to get me fatter? Bribing the teacher with candy already.
You the one that asked about
No, I want Portillo's, not caramels.
Hey, bud.
We'll talk. We'll talk when we get halfway through and see how hungry I am. All right, so I'm drawing more picture stuff here. Orange. There's my orange.
Yay.
So this is memory address 100, and I'm gonna jump by bytes. This is memory address 104, memory address 108, 112, 116. So AR is a variable that holds a memory address. That memory address is said to point to the beginning of the array in memory. Okay? Now, if I want to actually look at what's at bucket 0 of my array, I would say AR at bucket 0. Okay, this is the syntax for accessing a specific bucket of your array, and that's read-write. I can put stuff into the array this way, I can get stuff out of the array this way. What's going to be at bucket 0 in my array?
100.
No, that's just what he drew in the picture.
What lives at bucket 0 in my array right now?
It's going to be the address.
Not
I
that.
haven't highlighted, people. What's in here?
Nothing.
Empty blue box, right?
Yeah.
Nothing's in there.
So it's just
Okay?
gonna be the address.
So AR, why would it just be the address? There's nothing in here. Nothing.
Wouldn't it give you the address?
No.
at bucket 0?
No.
Oh, okay, never mind.
No, not the address. There's nothing in here. So when I say AR at bucket 0, I'm saying AR, follow your pointer to this bucket index 0, and there's nothing in there right now. Now the reality is when you first create this array in Java, in most languages, it does fill it with default values. What? Probably a 0. Never rely on default values. It's the worst programming mistake you can make. Because you never know if you're going to go to a different system architecture or different operating system where the default values change. Probably wouldn't. 0 is usually a pretty safe bet for integers. Never rely on them. If you want the thing to hold a 0, put a 0 there. Make sense? So when I run this, it is going to print out a 0 for me. There's my 0 because that's what it defaulted to. But for our intents and purposes, that array is currently empty. This whole structure, this whole data structure has been created for us from this one line of code. This guy right here set the wheels into motion for generating this setup. Make sense? All right. Now, I want to start putting crap into my array. So what I'm going to say is I'm going to create a quick little loop. For int I is equal to 0, I is less than ar dot length, I plus plus. And we'll say ar is equal, or ar at bucket I is equal to I plus 1. So we'll fill it up with the numbers 1 through 5. Okay. Then when we print out ar at bucket 0, it should be a 1. So what did this little loop here do? It went through and it put a 1 here, a 2 here, 3 here, 4 here, 5 there. Make sense? That's what that loop did. So now I have actual data stored in my array, indexed from 0 to that array dot length minus 1. So ar.length is the number of elements in AR, which will boil down to, in this case, 5. So this loop goes from 0 to 4, because we're going to keep going as long as I is less than 5. Make sense? Okay. So we have an index 0 to length minus 1, and then we have these addresses. Now, I'm going to print a couple things out here. So I'll put at bucket 3, I'll print out bucket 3 as well. So this is going to print out the 1, and it's going to print out the 4. Those two contents, right? This bucket 3 right here has a value of 4. All right. Now, how do arrays work? When I say something like AR at bucket 0, this actually gets translated into something else. Okay, it gets translated into something else. What it gets translated into is AR plus 0 times size of, in this case an int, because that's a type of thing in there. Well, what's the address of AR? 100 plus 0 times, what's the size of an integer? 4 bytes, correct? So we'll say 4. So that's 100 plus 0, which is 100, right? So this is going to say, when I say AR at bucket 0, it says, go to memory address 100, give me the value there. That's how the index is mapped into the memory address. Okay? Similarly, if I want AR at bucket 3, that's going to be AR plus 3 times size of int, which is 100 plus 3 times 4, which is going to be 112. Just so happens that bucket 3 lives at memory address 112. See how that works? Okay? So, when I say AR at bucket 3, I don't have to traverse this array. I just go to that memory address, because this guy right here is a math problem. That translates into the memory address that I need to go to now. Make sense? Okay? So, what I just explained there is why arrays are fast.
Because we have the direct address.
Well, because the address is computable. If I say I want to go to bucket 3, I go to bucket 3. I don't have to go to bucket 0, then bucket 1, then bucket 2, then bucket 3. I can just go right to bucket 3 because it's computable. Okay? Huh? Okay, memory inefficient because all of these things had to be right next to each other in memory. So in this example, we only have 5 integers we're storing, right? So total of 20 bytes. Not the end of the world. But let's say I'm going to store, I don't know, 1 million integers. So 1 million integers times 4 bytes, that's 4 million bytes. Starts adding up, right? So, and surely we can come up with larger data types than an integer. We have our primitive types we're talking about now, so we can bump it up to 64 bits if we want for longs. For doubles, we can bump it up to, doubles can take up 96 bits. I think it's, for a double, it's 64 bits for what comes before the decimal point, and then 32 bits for the after the decimal point. So I guess 96 bits is how the virtual machine handles doubles. So that's the biggest primitive type we can do. But we can create our own objects, and maybe our own object has, can store 500 different variables. So now you have an array of pointers which point to other objects, which are now taking up huge chunks of memory. All right. So bottom line is arrays are inefficient because they have to be stored right next to each other in memory, which is also the reason why they're fast. They have to be stored right next to each other in memory to make them fast. That makes it computable. If this went from 100 and this was at 194, I couldn't have computed bucket 3. I would have had to follow, kind of like go from point to point to point to point, which is what we're going to do with linked lists.
So the same reason make it faster, the same reason make it
memory inefficient. Now, just because something is memory inefficient doesn't mean don't use it, right? By today's standards, we have lots of memory. So storing even 1 million ints, we don't really care about, right? 1 million ints, that's, what do we say? That's 4. That's 4 million? Okay, so that's 4 million bits, correct? No, 4 million bytes. 4 million bytes. So we'll divide that by 1,024. So that's megabytes. Divide that by 1,024. That's, kilobytes, that's megabytes. So that's 3.81 megabytes of memory that we would need to take up to store 1 million ints.
That's 4 megabytes?
Yeah, a little bit less than 4 megabytes for 1 million ints. Not the end of the world, right? I mean, even those of you who have a budget pleaser laptop probably have a minimum of 2 gigabytes of RAM in your laptop, right?
But it's not that secure.
Huh?
It's not secure from the hacking, stuff like that.
Well, it's just local on your machine in memory.
Yeah.
So, at this point, the argument of security doesn't really come into play at this point. But, historically, the first computer I really started messing with, I started programming when I was 9, and I had a program made, a computer made by Epson. And I didn't know much about the computer. I just my dad got me a book, and I was just typing crap into it and seeing how it works. But I remember I got a 486 DX2 66 megahertz computer that had 8 megabytes of RAM. We had to wait for them to release the chip. This thing was bleeding edge. They weren't even running these things at NASA yet. It was an awesome computer. So storing 1 million integers would have taken up half of my system memory back then. So historic memory problems are a little different than modern memory problems, right? This is an MP3. That's what we're looking at there. That's an MP3. We're not going to miss 4 megabytes. Okay? So point there is that modern programmers, when I say that an array is memory inefficient, that doesn't necessarily mean that arrays are bad. But it does mean that you have to understand that about arrays so that when you're making a solution to a problem, you know whether or not that memory inefficiency aspect means something to you or not. If we're storing 10 numbers, I don't care how memory inefficient it is by today's standards, right? Doesn't matter. But if we're storing billions of things, now maybe it starts adding up, especially if those things that we're storing have large footprints. Now we have to start thinking about it. Okay? That makes sense? All right, so this is how arrays work. That syntax for creating an array is this. This would allow us to fill an array. This allows us to extract stuff from an array. So when this gets resolved, AR at bucket I says go to memory address AR plus I times size of this guy. That'll boil down to a memory address, and we're saying store whatever this value is there. Okay? So when we're filling it up, and I want to put something at bucket 3, that bucket 3 gets translated into memory address 112. Put that value at memory address 112. Human beings like to reference it as bucket 3. Computers are going to resolve that to the memory address. Make sense? Okay. So that's how arrays work. Now, another downside to arrays. What happens if we need to add a value to a full array?
Goes to the first one.
Well, if I fill this array up, so let's go back to my picture here. So it's already filled up with 1, 2, 3, 4, and 5. I want to put a 6 on there.
We have just one choice.
I'd love to do this.
You gotta recreate the
Yeah.
array, don't you?
But you already created the array.
Yeah, I need to build a brand new one. This is another way that arrays are memory inefficient. So let's just say you just built your dream home, and then you decide that you need to put in an addition. You didn't dream big enough. Okay, so you need to put another room in your dream home. Well, the way human beings solve that problem is we go in and add a room to the existing house. The way Java solves that problem is we abandon the house and build a new one with the extra room on it. Make sense?
Very inefficient.
Okay. That would not be smart in real life because that's expensive. Java does that. So that kind of gives us this idea of how memory inefficiency works. But even then, when we deal with computers, we don't care. Who cares? Right? Who cares how memory inefficient it is? So what we're going to do here is we're going to create an object. Let's see. They come up with an interesting name for our object. Magic buckets. Yeah, we'll create a magic bucket object. So we're going to name our object Magic Bucket. And Magic Bucket is going to allow us to create, well, under the hood, our Magic Buckets are going to be powered by arrays. Okay? And what Magic Buckets do is they allow us to store data. All right? So, for instance, the answer to this was build a brand new array and abandon the old one. You will likely need to copy everything from the old array into the new one and also make the new one a bit larger for more stuff. So that's the answer to that question. So we're creating a Magic Bucket object. The Magic Bucket object, this thing we're about to build, is going to be a tool for storing integers, storing ints. We should be able to store 0 ints up to infinity ints. It should provide methods to add an int to the front of the MagicBucket. Let me actually kick this down a line. Add an int to the end of the MagicBucket. Add an int at an index of the MagicBucket. And finally, display the contents of the MagicBucket. Make sense? Okay. So that's going to be our starting point for it. This is all the stuff this guy is going to do for us. All right? But at its heart, this guy is going to maintain an array of integers. And we're not going to worry about memory efficiency at all here. We're going to abstract this through a class. So inside of our MagicBucket, we're going to have a private integer array called the data. Okay? When we build our MagicBucket, it's going to take no parameters, and it's going to generate an empty array. Complete waste of time. We're going to do it anyways. That is, build me an array capable of holding nothing.
Why?
Huh?
Why?
Well, because I need to be able to add stuff to my array. Now, we could choose to start this guy off as null, so it doesn't hold any values. Okay? Then the very first time we add a value to it, we can say if it's currently null, that means we haven't set it up yet. Let's go ahead and set it. You can make either choice. We're going to be horrifically memory inefficient here in either case. Okay? But we'll do the null one. This is actually the null one will match up with what we're going to do with linked lists a little cleaner. So we'll go that route. So when we build a brand new MagicBucket, all we're going to do is we're going to set that field, the data, to null. And we'll go ahead and write our display method here. If the data is equal to null, empty MagicBucket. Else, we're going to display crap, right? All right, right now it's always going to be a null. So we technically have a functional object right now. We can create a brand new MagicBucket, passing it no parameters. It just nulls out the data, which was already null, but like I said, be explicit about default values. Don't just assume that this guy will be null by default. Okay? And then we can call this display method, which we know will always just display empty MagicBucket, because we have currently not put a way to put anything in there. So we'll go ahead and create one of those dudes. So we'll create an instance of our MagicBucket class, and then we'll tell this dude to display itself. And we'll get printed to the screen, empty MagicBucket. Make sense? All right. Now, we got some requirements we have to fulfill here. One of them is we need to have an add method that adds an integer to the front of the MagicBucket. That is, replace, well, after we call this method, whatever was at bucket 0 should now be at bucket 1. Because bucket 0 has now become this new value. Does that make sense? Okay. So we're going to call this guy going to be void. Okay, it's not returning a value. This guy's going to take an integer and store it at bucket 0 in our array, moving everything else over, right? Because we don't want to overwrite crap. We're adding to the front. So public void, let's call this guy addFront, and this guy's going to take an int val as a parameter. Now, what do I need to do? If the data is equal to null, that is, if it currently does not have a value, I need to go ahead and create a one element array and put at bucket 0 val. That's our easy case, correct? So then we'll say the data is equal to a new integer array, size 1, and then we'll go ahead and we'll say the data at bucket 0 is equal to val. That make sense? All right. Now, before we do any more of addFront, let's go ahead and fill in display. If it wasn't empty, what we're going to do is we're going to spin through that guy displaying the contents. Quick little for loop, parent I is equal to 0. Oh, and a quick little thing for those of you who are, this is your first time having me. I very likely program faster than you do. So that's why I record all my stuff, so you can go back and watch it so we can fit everything into the classes. So try to keep up. If I start losing you, raise your hand and say, hold on, what the heck are you doing there? Okay, but you know, I'm not expecting you to program at this speed, is what I'm getting at. If you can, then I can go home to my hot tub. And then you guys can come up here. But I'm going to venture a guess that I probably can program faster. Definitely than you. I knew that. That's why they made you a project manager.
Haters are my motivators. Keep it up.
All right. But I just wanted you to know my expectations. I'm not expecting you to be able to do this. I've been doing this for a little bit. What am I doing? Oh. The data.length, I plus plus. So we're just going to spin through every bucket of that array, and we're going to just print out whatever's at that bucket. So we'll say system.out.println the data at bucket I. All right, so now we have the else to our if in display. If we have nothing in data, the array is empty, well, the array is nothing, empty MagicBucket. Otherwise, spin through all the elements in it, displaying each one to the screen. All right, and now we've given ourselves the miniature ability of adding a single value to the empty list. Because we can add something to the front, and if the data was equal to null, which it will be initially, we'll then create data to be an array of one element and put at bucket 0 that value. So then we should be able to display something. Okay, so even though addFront isn't complete yet, we know we'll get into this if. So now I'll say mb.addFront, and let's add a 7, and then mb.display. All right, so we'll create our empty object, display it, add a 7 to the front, display it again. Okay, which should show us our 7. All right, there's our empty MagicBucket, and oh, now it's a 7. Cool. All right, now let's go back and look at the more, the less easy version of addFront. If the data was not equal to null, that means we already have an array, and it already has crap in it, right? This becomes problematic, because what we now need to do is, this gets back to our example earlier, we need to go and build a new house with one more room in it. Move all of our crap from our old house over to the new house. Put the new crap in the new room, and then we can burn down the old house. We have to physically do that in code. All right? So, else, we're going to create an integer array I'll just call it temp. And this guy's going to be a new integer array of size the data dot length plus 1. One extra bucket.
So the one usually goes to the beginning.
In this one, we're adding to the front. So val will go at bucket 0. So right off the bat, we can say temp at bucket 0 is equal to val. But now we need to copy all the contents of the data into temp from bucket. So bucket 0 of data needs to go to bucket 1 of temp. Bucket 1 of the data needs to go to bucket 2 of temp. So on and so forth.
For loop.
Yep, for loop, and then we'll put it to I plus 1. So for int I is equal to 0. I is less than the data dot length. I plus plus. And we'll say temp at bucket I plus 1 is equal to the data at bucket I. That makes sense? Now, what we just did here, so let's kind of draw this picture. I'm going to steal, I'll just steal this, and I'll make some modifications. So this was the data, correct? And let me actually just move these guys down here so I have access to them. So the data was null. Then we created it as a 1 array. And we currently have a 7 in there, correct? Now, when we want to add something else, we created this guy called temp. And temp is going to be a brand new array. Just because. Pictures are so fun. All right, so what we did is we created a temp like this. So we have 2 separate arrays. This is our new house over here. We can get rid of these guys. So this is our new house we just built, right? So what we first need to do is we need to copy whatever the value we're trying to add. So let's say we're going to add a 4 into bucket 0 of this guy. Then we need to go through every element of the data over here, copying. So bucket 0 of the data goes into bucket 1 of temp. So we'll copy that 7. So this is what that for loop is doing. And now we're done. We ran out of stuff from the data. But the data has not changed. So what we need to do now is we need to say the data is equal to temp. That is, the data points to the same place that temp points to. Does that make sense? So this is how pointers work. I am setting the data's value equal to 312. That is, making it point to the same place that temp is pointing to. In essence, abandoning this memory. Now nothing points to that memory. This guy is said to have a pointer count of 0. It used to have a pointer count of 1. Just the data pointed to it. But now that it has a pointer count of 0, automatic garbage collection that's built into Java will come and clean it up. Make that memory available for the new keyword to request later. All right? So the last thing we need to do in this method is we need to make data point to a brand new place in memory. So we literally just wiped out a house and built a brand new one to add that 1 value. So again, examples of memory inefficiency. So we'll add that last bit of code here. We're going to say the data is equal to temp. Make sense? All right. So now, create the new array temp, set bucket 0 to val, fill in the rest of it with the crap from the data, and then make the data point to the same place temp points to. So now I should be able to say mb.addFront for mb.display. And now it should display a 7, then a 4-7 for the new contents. And I should be able to call this a whole bunch of times. So, for instance, create my object. We're going to loop from all the values between 0 and 1,000. We're going to add each one of those values to the front individually. So we're going to destroy 1,000 houses. And each house is progressively larger than the previous. Okay? Ultimate memory inefficiency. And then we're going to display it at the end. Boom.
Sounds like the taking over of America.
Hmm.
Sounds like the taking over of America.
That's right. That's right. Now, initially, the size of memory was 32 bits. Right? 4 bytes. Then it was 8 bytes. Then it was 16 bytes. No, 32. No, 8, then 12, then 16. Jump by 4s. So, 32 bits, 4 bytes. So, but each time we added to it, we abandoned the previous chunk. See, the amount of memory we wasted here was a lot. Does that make sense? So in the end, we had a final array capable of holding 1,000 values. But one loop before that, we abandoned an array with 999 values in it. One loop before that, we abandoned an array with 998 values in it. So on and so forth. Make sense? Okay, so very, very, very memory inefficient. But still worked. Seemed to work fast, didn't it? Who cares? Arrays are fast. We just used our real estate agent to find us 1,000 houses. Like, go! We're destroying houses in this neighborhood. All right? So, that's addFront. Now we need to have a version called addEnd that puts something onto the end of the current array.
You're gonna destroy it.
Oh, we're still destroying it. Whenever we're dealing with arrays, we're always destroying. Because if you're going to put something on the end, our current array only holds what it currently holds. We still need to build the addition and then put something on there. Make sense?
So can we put something in the middle, like between?
That's this third guy. addAtIndex. All right. So, public void addEnd. This guy will take an int val. If the data is equal to null, then we'll say the data is equal to a new int array 1. The data at bucket 0 is equal to val. So the very same thing that we did for addFront, we'll do for addEnd. In fact, we could have just said this.addFront. So if it's null, we know it'll be null here, and we want the same crap to happen. We only saved ourselves a little bit of code there, but technically we didn't duplicate these exact lines of code more than once. So you can, I would call it a coin flip between just writing this if statement identically again and doing what we did here. Really doesn't matter. But just as an example of code reuse, we'll write it like this. Else. All right. So if it's not null, And that means I have an actual array I need to add something to the end of. Well, I know I'm going to be building a brand new integer array. We can call it temp. We know that array is going to be one bucket larger than the previous one. All right. Now, where are we going to put val? Val is going to go in the last legal bucket of temp. What's the last legal bucket of temp?
Length minus 1.
Length minus 1. So we say temp at bucket, temp dot length minus 1 is equal to val. Then we'll write a loop to copy everything from the data from bucket 0 to bucket length minus 1 into the equivalent buckets in
The new one.
the new one. So for int I is equal to 0, I is less than the data dot length, I plus plus, temp at bucket I is equal to the data at bucket I. Then at the end, the data is equal to temp. That makes sense? All right, so that allows us now to add stuff to the end. Go back into driver, test this a little bit. So we'll say mb.addFront 1. Then 0, mb.addEnd 3, mb.addEnd 4. It's good enough. So it should be 0, 1, 2, 3, 4.
What about display?
Then I got to do display.
Yeah.
So there's my 0, 1, 2, 3, 4. Actually, I never did a 2, did I?
No,
0, 1, 3, 4. Because I can't count.
exactly.
Perfect. All right. So, correct answer, bad counter. Make sense? All right. Again, very memory inefficient. All right. Lastly, we want to have a method that allows us to add something at a particular index. So this guy's going to take the value we want to add as well as the position that we want to add it to. Correct? Now, what if our array is currently null?
Then it should display empty, what you call it?
If I say add something to bucket 3 of something that doesn't have a bucket 3,
Would be 0.
No,
what's the appropriate thing to do?
tell it you don't have
Index
that
minus.
many buckets.
It's an error,
Yeah.
right? That would be a reasonable approach. Like, you want to add something to bucket 3? I don't have a bucket 3. Try again. Not do anything, right? Okay? So if it's null, it doesn't even matter what they passed us. There's no buckets to add stuff to. Does that make sense? What if they said I wanted to add to bucket 0? addAtIndex bucket 0 of the empty magic bucket. Should we allow them to add it to the front?
Yes.
Seems reasonable. So we'll have a couple of conditions here. We'll say if the data is equal to null, and, well, actually, we don't need to do that. If index is equal to 0, we'll just call addFront. Let it handle it. Let it handle creating the new array and putting it at bucket 0. Else if index is equal to, what if it's the last bucket?
Then have it go to add in.
Well, I guess what I'm saying, what if it's length? So what if I have something that currently has 5 buckets, 0 to 4, and it says I want to add something at bucket 5? Add something at bucket 5 says, I want to add something to the end.
Right. So we're gonna call.
Call addEnd. So if index is equal to the data dot length, then this dot addEnd val. Now we do need to be careful here though, because this line will throw an exception if our current array does not have data, because we will not be able to say the data dot length. That'll be an illegal call. All right. So what we can do is say if the data is not equal to null and index is equal to the data dot length, Java knows to check this Boolean expression first with an and, because both sides need to be true in order for the whole thing to be true. So if this is false to begin with, this side, it won't even try to call this. Make sense? All right. So if the index is 0, we're just going to go ahead and add to the front. If we're trying to add to the end, but the data is not equal to null, then we'll go ahead and call addEnd. What if the data is equal to null? Well,
Index equal. Say that again, sorry.
what if the data is equal to null? Is there a circumstance here where we would actually add something to the end? Or have we already covered that?
Yes.
The only legal case, if it was null and they were trying to add something to the end, they would say 0.
Right.
Correct?
Right.
Okay, so if index is 0, add front. Otherwise, as long as we have something and the length and what you're trying to add is in the end, we'll do it. Else if the data is equal to null, we wouldn't be in here unless we were not trying to add to the front and we were not trying to add to the end. If we're here, that means you were trying to add somewhere in the middle to something that was null. So we're going to go ahead and yell at them and just say, illegal index or something like that.
Explain last one.
Sure. All right, so this if statement here says if we're trying to add to the front, go ahead and add to the front. Whether it's null or not, addFront does the magic for us, right? This one says as long as the data does have a value and we're trying to add to one bucket beyond the end, then let's go ahead and add to the end. This one says, remember, I would only be here if both of these have failed.
Right.
Make sense?
Yeah.
So there's like a spill-through effect. So if I'm here, I'm saying, okay, otherwise, if the data is null, that means I don't currently have an array. And you've told me to add something somewhere other than bucket 0 or other than other than the length. Which means that if it is equal to null, you've told me to add something to an index that definitely does not exist. Correct? Because I have a length of 0 because I don't exist. I don't care what number you passed me. If it wasn't 0, it's a bad index. That makes sense? So we'll just yell at them and say bad index. Else if we're still here, that means the data is not equal to null. So it means we didn't get into this conditional. We didn't get here. We didn't hit here. So if I'm in here, I know that the data is a real array. But now I need to know if the index is either too small or too big. Make sense?
Yeah.
So if index is less than 0 or index is greater than
The data dot length.
the data dot length. Okay? If it's too small or it's too big, problem. Illegal index. Now, we could have done this as an OR off this if we wanted to. But I'm kind of a fan of spill through conditionals like this. I think this speaks better. Okay? You know, we could say something like this. We could maybe have these read a little different. So maybe instead of this saying illegal index, we might say what would be a reasonable error message? Don't be dumb. Yeah, there. That's don't be dumb. This one's an illegal index. Okay? So, else. Last one means it is a reasonable index. Correct? Now, we know that the index is not 0. And we know that the index is not that length. It's somewhere in between. So it's 1 to length minus 1. And if that's the case, we need to build the sandwich here. Correct? We got to do that work. So we're going to say int array temp is equal to a new int array the data dot length plus 1. Any way you cut it, we know it's going to be 1 bigger than the current one. Okay? Now, we know that temp at bucket index is going to equal val. That's that. We've already added the value to the right place. Now we need to move the other crap into the right spots without overwriting stuff, right? Okay. So we need to go from bucket 0 to bucket index minus 1.
So we're gonna do the same. We're gonna destroy and rebuild.
Oh, we already rebuild. We haven't destroyed yet. But now we've rebuilt. We've copied val into a certain position. But now we need to fill up temp with everything up to but not including index. And then everything from index to the end. To the rest of it. So the first loop for int I is equal to 0. I is less than index. I plus plus. Temp at bucket I is equal to the data at bucket I. So that'll copy everything from the beginning up to but not including index. Because we already have val in bucket index, correct?
Now from up to.
So now we need to say for int I is equal to,
Index plus 1.
got to start at index. It's got to start at index for the data. Because the index plus 1 didn't exist.
Right.
Okay? Because remember, the data has 2 halves right now. We just built the temp, which added a little bucket between those 2 halves. But data still looks like this. So we need to bridge across that. So we still need to go back to the data at bucket index and walk all the way to the end of data, but we need to place it at bucket I plus 1 in temp. 1 ahead, because we've already placed the thing at bucket index. So I is equal to index. I is less than the data dot length. I plus plus. Temp at bucket I plus 1 is equal to the data at bucket I. That make sense? All right, so we built our little sandwich.
Oh, wait, wouldn't index, I mean the IB, oh, never mind, I see what you did.
Yeah, let me show it in a picture here.
I'm losing it.
Well, it's kind of a hard concept actually what we're doing. So let me give Okay, and let's say we're going to add something. Let's make this a little bit. All right, so this is our current. This is our current the data. And we've decided that we're going to add a 5 at index 3. That's what we want to do. We want to add a 5 at index 3. Okay? So that means in our new one, bucket 3 is going to be a 5. Very first thing we do is we create a new array. It has one more bucket on it than the old guy. Something like that. Okay, then right off the bat, right, we're going to say bucket 3 is our 5. Okay, so what we just did there is we accomplished these 2 lines of code. So those 2 lines of code does this. Huh? Oh, all this stuff, all the ifs and stuff? Well, we didn't have to go through that in this particular case because we knew we had data. We're just looking at the algorithm for what we're solving here. So if we're in this else, that means all this other crap didn't happen. Make sense? We're going to want to test that, but for right now, we're trying to understand our algorithm here. So we went ahead and we put the value 5 at our new index 3. Now, first loop says to do what? First loop says to go from I to index, but not including index, copying each value from the data into the equivalent spot in temp. So that's going to take the 7 from bucket 0, copy it here. It's going to take the 4 from bucket 1, copy it to bucket 1 here. It's going to take the 3 from bucket 2, copy it there. Up to but not including index. Because this guy says less than index. Okay, so now we've accomplished what that for loop does. That for loop does this.
Question about the second for loop.
Mm-hmm.
Why didn't we? If you can go back to it real quick, please. Sorry, thank you. Seriously. All right. So why didn't we put the where it says temp I plus 1?
Mm-hmm.
Why didn't we put it inside the condition area where it has I equals index? We could have just put index plus 1, right?
No. I mean, you could have put index plus 1, but then you would have to say index minus, or you would have to say I minus 1 here.
Oh,
And you're going to see. That's why we're doing this. So we're going to start off at I at bucket index, which in our case is 3. And we're going to copy it into 4. So index plus 1, or I plus 1. So we're going to start off at bucket 3 here, and we're going to copy whatever's at bucket 3 in the data into bucket 4 of temp.
Gotcha.
That's where the plus 1 came from.
Which 4? No, I'm just playing.
Then we're going to copy the 8 from bucket 4 into bucket, now I get what you're saying, into bucket 5. Okay? Then the last thing is make the data point to the same place as temp. Make sense? Okay, so that does all the maneuvering for us. So as of right now, we have 0, 1, 3, 4. Ah, see, I did this on purpose. So I'm going to add a 2 to bucket 0, 1, 2. So mb.addAtIndex a 2 to bucket 2.
Aren't you clever?
Ha! 0, 1, 2, 3, 4. But now let's try to do some stupid stuff. So mb.addAtIndex 5 at index -3. That shouldn't work, right? Illegal index, -3. Let's try to add to index 9. Legal index 9.
What the one says right now.
It said don't be dumb. And that was one that had
So we'll do this while it's still null.
right.
Okay, so we're going to do it at the top here. So we're going to add a 5 to bucket 9. Don't be dumb. Right? We'll add a 5 to bucket -1. Don't be dumb. But if we try to add a 5 at bucket 0, it's going to let us do it.
Because
It just called addFront, right? We look at our code here. If index was 0, whether it was null or not, we just called addFront. And let addFront deal with it. addFront either would have built our array and put it to the front, or it would have added to the front of whatever was already there. Make sense? So we'll let addFront do the work. So that'll work. So we added a 5 onto the front initially, right? Then we added a 1 on front of that, a 0 in front of that, a 3 onto the end, a 4 onto the end. So we should have 0, 1, 5, 3, 4. Then the 2 actually goes in at bucket 2, so we should have 0, 1, 2, 5, 3, 4. Why does the 2 come before 5? Because we added it at index 2. And the 5 lived at index 2. Just was the order that we did stuff. Our code works so well, it's confusing. Go ahead.
if you want to remove something from the end, from the front, from the middle,
Mm-hmm.
do the same.
We do, and we're going to.
Let us read the homework.
You want that to be homework.
Hold up. Slow down. You already don't know what kind of homework we get. from
The
them.
homework's going to be
So
way
slow
harder
your
than that.
roll. Slow your roll. You trying to make stuff extra with him. He already extra.
He already
Bro,
extras.
Ali, warn him. Warn him.
But class is so entertaining.
It is. But the homework is not.
How are you going to learn?
By sitting here listening to you.
No.
watching
That's
and
being
following
entertained. You
along.
should be sitting here watching me code just like,
No. No, see.
like, how does he write so much code and it never has errors?
Yeah, it does.
We had an error yet today.
Yeah. That's because you keep erasing it before you finish it.
That's error-free code.
Whatever.
It's only an error if you hit the play button and bad stuff happens. I'm perfectly happy to have you teach.
No.
'Cause I could be in my hot tub.
Uh-huh.
All right. So now we want to add some more methods. Woo, hello. removeFront. removeEnd. removeAtIndex. So the complementary methods to those. And what the remove method should probably do is return the value it's removing. Does that make sense? We can choose as the person who's calling it whether or not we want to use that value. But we should go ahead and have it return it just for fun. So public int removeFront. It's going to take no parameters because we know where we're removing from. We're removing from the front, and it should return an integer. Now, what if the data is currently equal to null? Well, we can print that out. We can say system.out.println.
You're an idiot.
Don't be dumb.
Or
But wait a minute.
or okay.
Java's not happy. We advertise we're going to return an int.
So
You want to return a 0?
I mean, none.
no, you can't return a null.
It's an int.
Nothing is in a null.
Java makes us return something. We got a problem.
So how about you not make that an int?
Oh, that's the cowardless way out.
Look,
Modern day programming. What's the appropriate thing to do when somebody calls your code with something unreasonable? Old school programming would have been don't have it return an int or have it return a number that means nothing. But in our case here, we don't know what integers they're storing, right? You could return a -1, but maybe it was actually a -1. We might be returning the -1 that was at the front as opposed to a -1, which means bad stuff.
Retry. So there's a retry.
Okay? Give me an example of a retry from another programming language. Because in this, we're hard coding in the adds. I mean, I guess if we prompted them, what would you like to add? Or where would you like to remove?
Are you asking for it to recall that same function?
No.
Oh,
Well, you said retry. So, like, you would prompt them and say,
try again.
can't do that, try again.
Yep.
Right?
But that's still
Okay.
not returning an int.
Yeah, so here, that's just like us saying don't be dumb.
Right.
We could say don't be dumb, try again. You can even say that. A little smiley.
Or try again, stupid.
Well, I'll add stupid later to something else. I can't run out of words in one.
Oh, I have plenty. I work with enough stupid people where I can come up
You're a
with
project manager.
Huh? What'd you say?
That's it. All right, so don't be dumb, try again. Well, we still haven't solved the problem that we have to return an int.
Exactly.
You looking for useful information
Huh?
when you return something?
Well, I'm looking for how would a modern day programmer solve this problem. Historically, we would have had some sort of error code. We've experienced those, right? You go to a web page and bad things happen, it gets like, forbidden, 401 error or something like that, right? Okay. Well, in this case, we cannot do something like that. First of all, that doesn't make sense in our case, but for us, we don't know what integer we would be returning. There is no integer error code that's safe. 401 could be what was at bucket 0 of our list, of our array. So,
Transfer 20.
say this again?
Transfer 20.
To what?
20 dots.
You mean objects? Integer objects?
Yes.
So I can return a null?
No, you can.
Well, if it was an integer object, then I could return a null.
Okay.
That's still a cop-out. Modern day languages have something called exceptions.
Get exception.
We can raise an exception, and that allows us to bypass returning a value. So what I can do here is instead of this being a print statement, I can say this guy throws an exception. It's going to want me to did I spell exception right? Oh, we'll get back to it in a second. Let me steal this string. This should allow us to do this. Oh. We're fine. We just haven't finished writing the method yet. So if the data is equal to null, we're going to throw that exception. Else, just for right now, I'll return a -1 just to finish it. So notice it's happy now. All right. So it does require us in other cases to return a value or return an int. So if the data is null, we're going to throw an exception saying, don't be dumb, try again. But it threw an exception. And since our method advertises that it throws an exception, whoever calls our method must choose to deal with it in some way. They accept the responsibility of knowing that whatever they're about to call might throw an exception. That make sense? And we'll see this here in a second. Otherwise, if I'm removing from the front, I need to get the value that was at bucket 0, because that's the value I'm going to return. Then I need to downsize the array, moving everything forward 1. Bucket 1 becomes bucket 0, bucket 2 becomes bucket 1, bucket 3 becomes bucket 2, right? And then actually return the final value. So I'm going to say int val2 return is equal to the data at bucket 0. We know that guy exists because the data is not equal to null. Okay? So that's going to be the val we're ultimately going to return. In fact, we can go ahead and write this. Val2 return. But in between here, we need to do some stuff. Okay, so before we return it, we need to doctor our array. Now, what if the data.length is equal to 1?
No.
Yeah, we're just going to set it to null. The data is equal to null. If it was the length 1, now it's length 0, doesn't have anything in it. We're back to our initial state. So we don't have to move crap around. We'll just set it back to null. Okay? But before we did that, we did preserve the value we wanted to return. Else, if the length isn't 1, it must be bigger than 1. Therefore, we're going to say int array temp is equal to a new int array, the data.length minus 1, 1 smaller. Then we're going to say for int I is equal to 1, I is less than the data.length I plus plus. Actually, let's start off at 0. You can go either direction. Just that's more consistent with what we've been doing. We'll say temp at bucket I is equal to the data at bucket I plus 1. Otherwise, we would have said temp at bucket I minus 1 is equal to. Okay, so temp at bucket I is equal to the data at bucket I plus 1. So we'll move everything forward 1. And then ultimately, we'll say the data is equal to temp. And then we will return val to return. Oh, hold on a second. I had it in the right place. So if the data length is 1, we'll just null it. Otherwise, create a new array that's 1 smaller than the old one. Copy everything from the old one minus bucket 0 over to the new one. See, we're going to go data I plus 1, so it'll skip bucket 0. Set the data back to temp. So in either case, data is either null or it's to our new array. And in the end, return the val to return. And that's all the stuff that happens inside of our else. Make sense? All right. So this will remove something from the front. So our current code looks like this. And then we'll go ahead and we'll do a system.out.println mb.removeFront, and it's going to yell at us saying this guy throws an exception. So you must either wrap it in a try-catch, or we can pass the buck. Well, here, we'll wrap it in a try-catch. I'm too lazy to wrap it in a try-catch. We'll pass the buck. So we're just going to throw that exception on to somebody else. In this case, it's back to the Java virtual machine. So we're not going to deal with the exception. We just, thanks for letting me know. I'll let my program crash anyways. So, all right. So this will remove from the front. We should have it print out a 0. And then we'll do an mb.display again, which should show everything minus the 0. And let's put a little divider in there. Ruh-roh. My first error. All right, let's see what happened. We did return integer, but it said array index out of bounds 6. Oh, can't say length. We've got to say length minus 1. Make sense? We're looping through here. We loop through an extra time. So we create a temp to be 1 smaller than the data, but we loop through all the elements of the data.
Instead of that 1 minus.
Yeah. So actually, the way I was originally writing this would have avoided the error. Yeah, I had this to 1. Going less than that, I wanted to say temp at bucket I minus 1 is equal to the data at bucket I. This should work. So there's our, oh, do I display? Oh. So there's my original data. Here's me displaying the 0 I showed. Then here's the data afterwards, after removing the 0. Make sense? Okay. What about removeEnd?
I was just thinking it, but he said it.
Fine. 30 seconds, good? About 10 minutes.
Okay.
10 minutes? All right, we'll take a 10-minute break. Who?